In this section of chapter 11, I would like to discuss about intermolecular forces and phase diagram. Now, intermolecular forces exist between any molecule, and that's why if you cool down a gas sufficiently low temperature, you'd find that gas molecules would convert to a liquid because of those intermolecular forces. Think about water vapor. See, these are the water vapor. In vapor phase, these molecules are all free. As you cool down, there'll be their attractive forces. Try to hold them back and allow them to condense to liquid phase. So there are different types of intermolecular forces, and that's what we are going to discuss here. After that, we'll talk about phase diagram. In ionic type of intermolecular forces, basically you need to have ionic substance, like sodium chloride, which forms sodium plus and Cl minus ion. So the type of force existing is ionic force. The second kind is called ion dipole force. Like you have ionic substance, say, is dissolved in water. Water is a dipolar substance having a dipole moment. So it's called ion dipole intermolecular force. Here we are going to discuss about dipole-dipole intermolecular force. So you must have a polar molecule like methyl chloride. Methyl chloride looks like this, CH3Cl. And carbon is less electronegative than Cl, so there is a pull of electrons towards Cl because Cl is more electronegative. And that gives rise to a negative end and a positive end. And that's what we are showing you here. And these gas molecules, they attract each other because of this kind of charge distribution, plus, minus, and then the minus end faces the plus end. And that's how these molecules get organized and form liquid from gas phase. The fourth type of force is called London dispersion force. It is usually the weakest of all the forces that we discussed, and this exists as a major force in nonpolar molecules. So you think about intermolecular forces in nonpolar molecules, you think in terms of London dispersion force. More polarizable molecules or atoms show greater attraction. Like in case of noble gas, argon is a lot more polarizable than say neon because you are getting bigger and bigger atom with more and more electron shells added to it. And that allows greater polarization. Now let me explain to you what polarization is. Say one argon atom approaches the other argon, then there'd be negative on one end and positive induced on the other end. How? Electrons repel each other. So as they get closer, electrons from the right hand side argon would go to the farther end. So in other words, its end that is facing the other argon would have delta plus if the first argon comes with delta minus or negative charge. So second argon would have minus charges to the farther end because they're repelled. These electrons are repelled from the incoming argon. So this coming approaches and electrons will be getting farther away from the approaching argon. And that's how negative charge concentration would be on the right hand side of second argon atom. Hydrogen bond, this is a very important type of bonding, especially in water. You'd expect hydrogen bonding in compounds where you have nitrogen, oxygen, or fluorine. So if I have OH, that gives hydrogen bonding, which I'm showing you as an example at the bottom. Hydrogen acts as a bridge in making bond between two water molecules. And you can have more than a number of hydrogen bonding in the liquid or even in the gas phase. Say for example, with this oxygen also I can have a hydrogen, then oxygen and hydrogen. So anyway, when hydrogen is bonded to nitrogen, oxygen, fluorine, you would expect hydrogen bonding. And this is a strong type of intermolecular force. Now the phase diagram. Phase diagram explains under different temperature and pressure condition what kind of a state of matter you'd have. Now what you're looking at now is the phase diagram for water, and you can see along y-axis you have two different pressures are shown. The other pressure, of course, you can estimate based on the given pressure values. Normal melting, let me show you that. First, let me explain to you what are different types of curves you have. The solid straight line, let me show you in blue, that represents solid liquid equilibrium. In other words, it would define melting points depending upon what kind of outside pressure you have. So that gives melting. On the left hand side of that you get solid. On the right side you have liquid. Solid in this case is ice. Liquid would be liquid water. If I increase temperature, say for example we pick the value here, that we'd be calling normal freezing point, because under atmospheric pressure solid liquid equilibrium is called normal freezing or normal melting point. If I keep on hitting it, you are following the dotted line, you reach this curve, the second curve. On the right hand side you have gas, on the left hand side you have liquid. So on this curve, this point represents liquid gas equilibrium, and that's boiling under 1 atmospheric pressure. And the boiling point, boiling temperature under 1 atmospheric pressure is called normal boiling temperature, and that would be 100 degrees centigrade, which we all know in case of liquid water. So the second curve I'm going to draw in red. This second curve shows liquid vapor equilibrium curve, or basically different boiling temperature curve. As you increase outside pressure or decrease outside pressure, boiling temperatures are going to be different. So you follow the curve and that will let you find out the boiling temperature. Say for example you're supposed to get normal freezing point. What you're going to do is draw that line along 1 atmosphere and go vertically down and read the temperature along the x-axis. These are not all done in scale, so we could be off, but in case of boiling you get down. In order to answer any question on these kind of phase diagrams, you'll have to look at the actual phase diagram given in the book, but I'm pretty much giving you the idea how to get these temperatures. So once you get vertically down, once you get where the 1 atmospheric pressure line intersects that solid liquid equilibrium line, so then from here, from x-axis, you get the melting point or freezing point. As I told you that you should not go by this particular curve because this is not drawn to scale. And in order to get the boiling temperature, you follow this and go and read this temperature that I'm showing you on the x-axis. Now, if your temperature and pressure is such that you are in this area, that would represent liquid state. On the far left, that would represent solid. So whenever you have third curve, let me show you which curve I'm talking about, which is solid gas equilibrium curve. That's curve. I'm showing you in green. On the left hand side of that green curve, you have solid. On the right side, you have gas. So it's called sublimation. Solid directly changing to gas. So that would happen at a pressure lower than 4.5 torr. So somewhere here. So it doesn't go through as you heat any solid below that pressure, and there'll be no solid to liquid conversion. It'll be solid directly going to gas. All these three curves intersect here. It's called triple point. Solid, liquid, and gas. All these phases are in equilibrium. So keep that in mind. And so that's basically the phase diagram. And also there is the maximum temperature. If I keep on increasing, say for example, and there is the maximum temperature you're going to reach. After that, there'll be no liquid existing. That's called critical temperature. So above the critical temperature, you'd only have gas. There'll be no liquid, no matter how high is the pressure that you apply. So here we're showing you phase diagram for carbon dioxide, not drawn to scale, just only some of the numbers are I have copied so that I can explain this to you. You can try this homework problem, problem 7 from page 454. In a different section, I would go over that problem also. So here I just wanted to remind you this. The critical point is that point where solid, liquid, and gas coexist. Below triple point, solid would directly convert to a gas. Below triple point is these, any point below this. So solid would go directly to gas. So that's sublimation. And this line I'm showing you in green would show you pressure effect on melting. It can be tilted to the right or it can be tilted to the left, as in case of ice. When it is tilted to the right in this case, in case of carbon dioxide, as pressure is increased, so you can think about it. If I increase the pressure, look at what happens to the melting point. Melting point is also increased. On the other hand, you'd see the reverse thing in case of water, where this solid liquid curve is tilted towards left. In that case, just the reverse thing you are going to see. As pressure is increased, let me show you. This is one freezing point. This is the second freezing point. As pressure is increased, freezing point decreased. And that's the case in case of ice.